Hey guys, here is another episode of Coronavirus Chemistry, and as you can see, I'm at home. I'm not sure, I don't think I've made a video at home for you guys yet in Chemistry 1, but here I am. I'm at home and we're making videos about the next unit. So remember that the last unit was stoichiometry, and we're going to be using that pretty much the remainder of the year in many different ways, particularly since we now know how can we calculate the amount of reactant or product necessary to do a reaction and that kind of stuff. But our next unit is thermochemistry. Thermochemistry is really the chemistry of heat. So, for example, like a hot-cold pack that you have when your muscles is aching or something like that, you break the seal between the two sides, and then the mixture combines, and you get this either warm sensation or cold sensation, depending on what kind of pack you bought. There's chemistry involved in that. There's chemistry in when you mix things and heat is either released, or sometimes heat actually goes into the reaction and actually feels cold in that way. So we are going to be discussing the process of the way in which heat is involved. Physical heat is involved in chemical reactions, and that's our next topic. So let's go ahead and just dig in. The first day here, this is March 30th, I think. Yeah, we're March 30th. I'll just double check there on my computer. Yeah, we're March 30th. Wow. I do not know how much longer this is going to last. I know Governor DeWine has put into place some more restrictions on people moving in and out of the neighborhoods and stuff like that, and things are crazy. Things are absolutely crazy. I don't know when we're going to hear anything about this last week and if we're going to continue on with this online learning or not. But whatever happens, we're going to keep pushing through. We'll be okay. We'll be okay. So let's go ahead and just get some basic things out of the way like I did with the last videos, where I just kind of go through things with a piece of paper. So heat. So I want to define heat for you. Heat is the amount of energy in a chemical system related to molecular motion. So molecules moving around, hitting each other, spreading apart, moving at a certain speed. Either they're moving very slowly or they're moving fast, going around rapidly. Just looking at this diagram I built here, so let's say we have particles A and B. Which of these has more heat? Well, this particle is moving at a speed of 1,000 meters per second, while particle B is moving at a speed of 10 meters per second. We would say that particle A has more kinetic energy. You may remember that kinetic energy is a way of measuring how much motion or how much energy is in the motion of an object. You might have learned that in a physics course. Particles, little tiny molecules, atoms, they're matter. It doesn't matter if we're talking about a bowling ball or a tiny little particle. There is kinetic energy in something moving, in matter moving. So this little particle, while it's the size of, infinitesimally smaller than a pinhead, this is really, really fast, and it still has a lot of kinetic energy, because kinetic energy is 1/2 mv squared, 1/2 times the mass of that particle times the velocity squared. So this particle has more kinetic energy, and in that it has more heat. Heat is defined by how much motion the particles are in. And we can relate that to temperature. And there's really a really cool way of relating all these different things. If you ever wanted to take AB chemistry, I go through how heat and kinetic energy and temperature are all interrelated. But for another day maybe. But we would say that this particle A, has more heat because it has more kinetic energy, because it is moving at a higher speed. Now, when particles are in motion, they can interact with the surroundings. So, for example, let's go ahead and move this down a little bit more. We may have a situation, pretty standard situation, where we have a hot plate and we have a beaker of water on there. Now, that hot plate, if I turn on the hot plate and I get the water heated up, the water eventually is going to boil. So it's going to go through this process right here of going from a liquid state to a gaseous state. And the process that's taking place, this right here, is what is known as the chemical system. The chemical system is the reaction that's taking place, and it includes all of the particles that are in that chemical reaction, either the products or the reactants. So in this case, a very simple reaction is just going from the liquid phase to the gaseous phase. We would consider the system to be the liquid water molecules and the gaseous water molecules, the steam that forms out of the boiling water. Now, that chemical system is contained. It's contained in the beaker. And also, above the beaker is the atmosphere. It's just the air that the steam is going to go into. Now, the surroundings is what we call those things. The surroundings are the container that holds the reaction and everything also around the reaction. So the atmosphere, maybe the table that the reaction is on. In this case, the reaction is happening on a hot plate. But the surroundings are everything that contains that reaction, that chemical system. These are some terms I'm going to be using a lot in that the system is either going to gain heat, the system might lose heat to the surroundings might give heat to the system. So there's always this interplay, interplay of heat moving between the surroundings and the system. So for example, with this one, the water molecules are receiving heat from the hot plate. The hot plate is being heated by electrons moving through a coil down here, and that heats up the top of the hot plate, and that makes heat move from the hot plate into the beaker first, really, and then the water, the liquid water. And then the water molecules receiving that heat start to move around really, really fast. And then eventually they move around so much that they escape out of the liquid state and go into the gaseous state, becoming steam. So the heat is exchanged from the hot plate, the base of the hot plate, to the top of the hot plate, to the beaker, and then to the water. And then eventually, the water is going to be steam, and the steam has some heat, and then the steam is going to exchange heat energy with the atmosphere as well, the air up here. And so that kind of happens with everyday situations. In the morning, you may see dew forming on the grass. That's essentially just, there was gaseous water in the atmosphere. We can't really see it very well, but as the temperature drops during the night, it condenses back into liquid and then falls upon the grass. So there's always this exchange of heat. Either heat is going to go into things, or it's going to be the heat is going to be lost by something. And that really goes into the next big topic there, which is heat exchange terms. So I'm going to be using some terms. You probably heard these terms before to talk about how heat is being moved around. And I'll just kind of reiterate what I just said. So if a particle like A right here is moving with a speed of 1,000 meters per second, and it knocks into particle B, you could think of this as like, the liquid water in our previous example. It's going to be smashing into the glass that is the beaker. So this is the water particle, and this is the beaker. So the water is going to keep hitting against the beaker over and over again. And there's some transfer of heat there, because that's just how things work. If you throw a bowling ball down the lane, eventually it knocks over the pins. There's energy exchanged by the bowling ball hitting the pins. In the same way, a particle like a water particle can hit a beaker particle, and there's going to be exchanging heat. The energy is going to be shifted. You notice this a lot with glass. Beakers will, if you're really, really hot, you can put them on something cold and they'll shatter. Sometimes that's happened in lab. Our beakers are designed so that doesn't happen, but it can. There's a rapid exchange of heat, and that can crack the glass. So in this situation, A is transferring excess heat to B. And so if we think about a reaction happening in solution, in a dissolved aqueous solution, the reaction particles, like we just dissolved sodium chloride in water, there's going to be ionization that takes place. And that ionization, let me draw that. So if I put NaCl, the reaction is going to be the sodium and the chlorine becoming ionized. Now, the sodium and the chlorine ions are surrounded by water molecules. That's the surroundings for the sodium and chlorine ions. So in doing this, there's going to be some exchange of heat, because that process of becoming ionized is going to cause particles to separate, and then they're going to smash into each other, bounce around, and hit each other a bunch of times. And either the water is going to give heat to the ions, or the ions themselves are going to give heat to the water. And then when you hold this flask in your hands, it may be cold or it may be warm. That's the process of heat exchange. So heat can either go into the reaction or out of the reaction. The reaction is the system. The system is where heat is either going into or out of. And two terms we're going to use to describe that process of heat being going into something or going out of something. So these two terms, hopefully you've heard them before from biology probably, exothermic and endothermic. An exothermic process is when heat is released out of the system. Heat is going to go out, away from the system. And then endothermic, endo means inside, exo means out. Endothermic, heat is gained and goes into the system. So this may be a situation where, like with this situation here, the water molecules actually are going to hit the sodium and chlorine ions, and then that gives the chlorine and sodium ions extra heat. That would be endothermic. If this process was reversed, I don't remember whether this reaction is endothermic or exothermic off the top of my head, but if the chlorine and sodium ions gave heat to the water, that would be exothermic. Now, if a reaction is exothermic, it feels warm in your hands. That's because those dissolved ions or whatever reaction is taking place releases heat, and then whatever container that reaction is in is going to feel warm in your hands because the reactant molecules are doing their thing, forming products, and then heat goes out, and you feel that warmth. Endothermic reactions are going to feel cold in your hands because in order for the reaction to take place, extra heat is necessary. And so the reactant molecules are actually going to draw in heat from the surroundings, and then the surroundings are going to feel cold. So the water in the flask, and then ultimately the flask itself, is going to feel cold in your hands because heat is being pulled from the water and into the reactant particles that are doing the reaction. The phone just vibrated. I'm just going to double check it. Everyone's good. So those are the terms that are really, really helpful when we talk about what's happening here. Now, how do you measure heat? That's the next question. How do you measure heat? Well, when heat is exchanged, there's going to be a change in temperature. Things like the water or the beaker or the reactant particles are going to change in temperature. We measure heat by measuring temperature in degrees Celsius. We can measure temperature using, of course, a thermometer. So to measure the heat, we have to have a change in temperature. Now, this equation right here is how we measure the heat. That's energy. Energy is heat. Heat is energy. Temperature and heat are not the same thing, but they're correlated. Now, to measure how much heat has been exchanged, we can use this equation. Q equals mc delta T. Some people like mcat. That's kind of cool to say. mcat. Q equals mcat. So heat measured in joules, let me pull that up a bit more. Heat measured in joules is equal to M. M is the mass. So if something is, like if we take a ball or something like that, heat it up, and then put it in a bunch of water, that is going to be an exchange of heat. We're going to talk about the mass of the ball going in the water. So that mass of the thing going in the water is what we're talking about when we talk about mass. And that's going to be multiplied by c. This is not the speed of light. This is another c. There's a lot of same uses of the letter throughout chemistry. This is known as the specific heat. The specific heat is a constant. And let me pull this up a bit. It's a constant that tells us how much energy in joules, so joules per gram Celsius, how much energy in joules is necessary to raise 1 gram of that substance by 1 degrees Celsius. The specific heat of water, which we use a lot, is 4.18 joules per gram Celsius. That's a pretty big number, actually. Metals have very low specific heats. It only takes, I think, like copper, I think, is like 0.9 joules per gram Celsius. Copper is really bad at holding heat. Metals, in general, are really bad at holding heat. They like to take heat in and then spread it away as quickly as possible. That's why you use copper and steel and things like that for cooking, because the heat coming from your burners, that immediately transfers quickly off of the burner into the pan and into the food. If you used something else, like, I can't think of anything right now, but water would be a very bad idea. Water is very bad at exchanging heat. Water is very good at holding in heat. Some of you may be really good at computer stuff. Water cooling. The reason why water is used in cooling CPUs and computers is because water is really good at holding heat before it changes temperature. It takes a little more than 4 joules of energy to change 1 gram of water by 1 degree Celsius. Something metallic is not good at that. One thing with computers also, heat sinks are made of copper. Same thing, the heat sink takes the heat really, really well from the CPU, but then there's a big fan attached, and that fan blows the heat off of the heat sink as quickly as possible. But the water cooling is designed so that it's constantly circulating and processing that heat and then exchanging it with the metal and stuff like that. But water is really, really good at holding energy before it changes temperature. That's why water is a good insulator and used in water cooling. Anyway, back to the equation here. So MC and then delta T. Delta means change in. It's a Greek letter. Means change in. So it's a change in temperature. So it's the final temperature minus the initial temperature in degrees Celsius. One thing also to keep in mind is the value Q. So if Q is a positive number, that means that heat went into the system. So if it's positive, there's a gain of energy by whatever we're talking about. So that would be a system that changes temperature in the positive direction. So it starts at 20 degrees and then goes up to 90 degrees or something like that. So the heat is gained by that object or that system, whatever you want to call it really. When that is a positive value, the reaction is endothermic. So like my idea with the ball going into the water, if the water was really, really hot and the ball was very, very cold, the water is going to heat up the ball as it goes in the water. So the water is losing heat to the ball and the ball is gaining heat. So that's a positive value of Q. So it's going to be endothermic for the ball. It's exothermic, though, for the water because the water is losing heat. So when Q is negative, when you lose heat energy, heat is going out of the system, and therefore the reaction is exothermic. So if something is endothermic, there's a positive Q. If something is exothermic, it's a negative Q. All right, let's go ahead and dig into doing some math with this. So pretty straightforward question here. How much heat is gained by 20 grams of water when its temperature is raised from 25 to 75 degrees Celsius? All right, so we want to know just how much heat is being gained by the water. So we just have like a flask of water, and it's sitting on a hot plate, and it's being heated from 25 to 75 degrees Celsius. How much energy is used to do that? So we're going to use this equation, do it, Q equals MC delta T. So Q is going to be equal to 20 grams of water times the specific heat of water, which we just learned is 4.18 joules per gram Celsius. And then we are going to multiply by the change in the temperature of the water. The water initially was 25 and it ended at 75. So that'd be 75 minus 25, so a change in temperature of 50 degrees Celsius. Okay. When you look at the equation, you can see that the unit at the end is going to be joules. How do you know that? Well, grams is down here in the denominator for this unit, so grams goes away. Celsius goes away, it's also the denominator here, so the only unit left over is joules. So our answer is going to be in joules. And so Q is going to be equal to 20 times 4.18 times 50. Let's go ahead and put that on our calculator here. So 20 times 4.18 times 50, and we get 4,180 joules. That's okay. There we go. So that's just a straightforward use of MCAT. You got to know the mass of the thing we're talking about. We got to know the specific heat. We got to know what the change in temperature is, and we can find how much heat is being exchanged. Now let's take this a little bit further. So we take that heated 20 grams of water. So in that previous problem, we had 20 grams of water heated up to 75 degrees Celsius. And we're going to pour that water into another 20 grams of water, which is at 20 degrees Celsius. What temperature will the resulting 40 grams of water be after pouring? So we're taking this water, which is at 75 degrees Celsius in our previous problem, and we're going to put it into another glass of water. This water is at 20 degrees Celsius. We want to figure out, well, at the end of this mixing, what temperature will the whole water be? That's really easy to do, and you can do that with MCAT. Now, the big idea here to keep in mind is this: the law of conservation of energy. Heat energy is neither created nor destroyed. It does not mysteriously vaporize. It does not become cold-ons or hot-ons or any weird thing like that. There is energy, and it transfers between things. It does not go away. So energy is neither created nor destroyed. It's only transferred. So that can be transferred by friction. It can be transferred by particles hitting each other. That's friction, really. But really, at the end of the day, it's just particles hitting each other, and then there's an exchange of heat, and the particles have the same. The total amount of energy stays the same. Never, ever goes away. Now, we're going to go ahead and answer this question. Well, how much water, what the temperature is going to be for the water at the end. Now, I'm going to still use Q equals MC delta T. Go ahead and plug that in there. Now, this water we just calculated had 4,180 joules of energy to it. At that temperature, it has 4,180 joules to it. That energy is going to go into this water right here. But the water is not, we're not putting this 20 grams isn't going to stay alone now. It's going to be 40 grams of water altogether. So Q is going to be that, 4,180 joules. That's how much this water is gaining. And that's going to be equal to the mass. So the mass of both of these waters combined is going to be 40 grams. The water is still 4.18 joules per gram Celsius for specific heat. And then we don't know the final temperature of the mixture. So I'm going to leave it as T subscript F for T final. Now the initial temperature of this water is 20. So this is an algebra problem. I know the initial temperature of the water, and I know the mass of all of the water, and I know the specific heat. I know how much energy this water is going to give to the 20 grams here. So let's do the math. 4,180 equals the 40 times 4.18 for right there. Okay, so 167.2, and then I'm gonna go ahead and do this real quick. I'm running out of room. So that's these two numbers together, and then I would distribute, right? So I would distribute to everything in the parentheses here. So 167.2 times TF, and then minus 167.2 minus 20, so it's going to be times 20 for the distributes there, 3344. Okay. And then we're going to do the math. So add 3344 on both sides. Adding that to 4180, 7524, 7524. Divide by that on both sides. Okay. So the final temperature of this water is going to be 7524 divided by 167.2, and that's 45. And that makes sense. It makes a lot of sense. So this water was 75 degrees Celsius. This water was 20 degrees Celsius. It's going to be somewhere in the middle when it mixes, the temperature. So 45 degrees Celsius is the answer. A lot of this stuff really is just common sense. You know that if you put hot water into cold water, it doesn't get colder. It gets warmer. This water right here would get warmer. So if you get a number like negative 20 degrees Celsius? That doesn't make any sense. I've seen people do that kind of stuff a lot in chemistry. They just kind of plug numbers in and see what happens. Use common sense. So hot water going into cold water makes this water get warmer, makes this water get colder. So it's going to be somewhere in the middle. 45 degrees Celsius makes a lot of sense. Nothing else can really be done there. All right, last question to go through here. This one has to do with what I kind of said a moment ago. Let's say we want to find the specific heat of copper. So let's say we have a situation like this. Let's say we have a copper ball right here, and it's been in an oven, and in that oven it goes from 20 degrees Celsius up to 1060 degrees Celsius, and then that copper ball, which is 5 grams, is going to be deposited into a 50 milliliter water container. And then we measure the temperature with a thermometer and find that the temperature of the water went from 20 degrees Celsius to 30 degrees Celsius. Now with that information, we want to be able to figure out what the specific heat of the copper is in this scenario. One thing to keep in mind here is this. So there was an exchange of heat, right? The copper, which was very, very hot, went into this water, and the water heated up. The copper then would have cooled down. It would have actually cooled down all the way to 30 degrees Celsius. It went from 1060 to 30 degrees Celsius. And remember, there's the law of conservation of energy. So the amount of heat that the water absorbed is the amount of heat that the copper gave to the water. I'm going to write that down. So the Q of the water is equal to the Q of the copper. So the amount of heat that was exchanged between the two is equal. The water gained energy, the copper lost the energy. Now what we can do now is we can figure out what the value of C is by doing this. And I'm going to split this. Q is MC delta T, so I'm going to do that for both sides. So Q equals MC delta T for the water. Oh, one thing here. So a lot of students, 50 milliliters of water. What's the mass of 50 milliliters of water? Well, the density of water is 1 gram per milliliter. So this is 50 milliliters. That means the mass of the water is 50 grams. So 50 grams of water times the specific heat of water times the change in the temperature of that water. So it's 30 minus 20 equals, and then the mass of the copper was 5 grams. I don't know the specific heat of the copper. I'll leave it as C. But I know that the temperature of the copper ended up at 30. So final temperature was 30. It initially was 1060. Some students, they think, oh, the 20 is important. It doesn't matter. So it started at 20 in the very beginning of this whole situation, but the exchange of heat was only between the 1060 and the 30 degrees Celsius. So its final temperature was 30 in the water, and it started at 1060. So now we do some math. So right here, we can just do all that at once. 50 times 4.18, and then 30 minus 20 is 10, so times 10. So 2090. Okay. Now, one thing to keep in mind too is this. Notice how I put a negative there. I did that for a reason. So the water gained the heat, but the copper lost the heat. So I'm going to put a negative sign right there in my calculation. I forgot that a moment ago, but I have to put that in there because the copper lost the heat, the water gained the heat. So 2090 equals, and that would be negative 5C, and that 30 minus 1060, go ahead and do that. 30 minus 1060, you can do that in your head if you want, and that's minus 1030. Okay, so a little algebra there. 5 times 1030, that's a negative number there and a negative number there. So we're going to have 2090 equals, and that's going to be 5150C, okay? And then we can divide on both sides. So the specific heat of the copper is going to be 2090 divided by 5150. Put it over there so you can see it. So 2190 divided by 5150 equals 0.4. 0.4, let's go ahead and give 3 sig figs, 0.406. So 0.406 joules per gram Celsius. That's the unit for specific heat, joules per gram Celsius. We'll bring that up there. And that makes sense. It's a metal. Metals are very bad at holding onto heat. You can think of specific heat as how good, bad grammar there, how well a substance holds heat. Metals are very bad at holding heat. They have usually very low specific heats. Things like water, any sort of liquid really, things like that are usually pretty good at holding heat. And so their specific heats are going to be a lot higher. But for the copper, it makes sense, 0.406. Always double check your math, of course. And that's about it. We'll talk more about this in the coming days. I hope to be making more videos in the next few. I'll send out more announcements about what's going on. There are some questions already online for you to answer. As I said in my message a week ago, I am not checking to see if you got these right. I'm hoping that you did them right and that you are learning from it. But if you have any questions, let me know, and I'm happy to help you out. Bye.